I'll be helping another YouTuber, Melissa Lucy, prepare for her next exam. And I've even created a free study plan that you can download using the link in the description. That study plan has several videos or other resources that I personally recommend for you. All right, let's learn how to draw Lewis structures properly. So today, we're basically going to be focusing on how to draw Lewis structures. I know that there's so many questions that you're thrown with Lewis structures where they expect you to know, one, how to draw it, and then, the geometries, resonance, all of these other words that we're going to learn later on. But for now, let's at least get a good foundation of just understanding how to actually draw the structure, because that's I'd say that's the most important part, because if you don't have that right, then everything else is wrong. So no pressure, but let's focus on just understanding this. So we've talked about this before, looking at valence electrons, and I know I went over this a little bit where I was just talking about what is a valence electron. It's the electron that's on the outermost shell of an atom. And really what I want you to memorize is everything that is highlighted here. So just knowing that this group only has one valence electron. The next one has two. We're not going to look at anything to do with, transition metals for Lewis structures. And then the next one would just be, this column is going to be 3 valence electrons, 4, 5, 6, 7, 8, you get the point. But it's going to be really important to actually have these memorized. So some of the most common atoms that we're actually going to see that we're going to use, I'll just highlight them real quick. So definitely hydrogen, that's going to be something that's really known. We're going to see that so much. Carbon is one of the most used atoms, I would say, that we're going to use for Lewis structures. Same goes with oxygen. Same goes with, let's see, nitrogen. And then we probably are going to see some fluorine, chlorine, sulfur, and pretty much a lot of just the nonmetals. Because the whole concept here with Lewis structures is the ones that we typically see are covalent Lewis structures, meaning they share electrons, and it's all nonmetals. All right, so if we remember that concept, going from ionic compounds to covalent compounds, ionic compounds consist of one metal and one nonmetal, and then they're actually transferring electrons, versus covalent compounds, which are sharing electrons, and they also consist of just nonmetals. Okay, so I think we're okay with that. Let's just start off with all the different steps of how to draw a Lewis structure. So first things first, we're going to have to know every single valence electron. So carbon has how many valence electrons, and then same with hydrogen. And then we're going to add all of that together. So kind of going back from memory, or you can look at your periodic table, how many valence electrons does carbon have?
Carbon has 4.
Cool. I'm gonna write it up here. So carbon has 4. How many valence electrons does hydrogen have?
1.
Perfect. And then we would multiply this by 4 because this subscript is telling us that there are 4 hydrogens in the structure. So that would give us 1 times 4, so 4. Then the next thing is just to add everything together. So I would add just 4 plus 4 to give us 8 valence electrons. So first step is done. All I have to do is calculate the total number of valence electrons. We said it was 8. The next thing is identifying which one is going to be the central atom. So for the central atom, I know this one's kind of obvious because there's 4 hydrogens, so that has to surround the carbon. But just to note, carbon will typically always be, or actually it will always be the central atom if it is in the structure. Okay, so carbon, number 1, that's always going to be in the center. Now, if there wasn't carbon in the Lewis structure, then it's going to be the least electronegative. So the least electronegative atom would be your central atom if carbon isn't there. Okay. So it doesn't apply for this case because hydrogen is never, and also that's actually something to note, hydrogen will never be your central atom because it could only have 1 valence electron, meaning it's only going to be able to create 1 bond. Is this making sense so far? I know I'm throwing a lot at you. So
yeah, but when you say least electronegative, if we were comparing 2 and we're following that trend, then the one opposite of the trend, is that what you're saying when you say least?
Correct.
Or okay.
Correct. If I were to have something I don't know, like this, and then you were asked oh, what's the central atom? And I know they're not going to be given this exactly, but we'll do an example. But from there, you would see, okay, which one is the least electronegative compared to chlorine and fluorine? Well, that would be chlorine. So chlorine would be your central atom. Does that make sense?
Oh, yes, because it goes up and to the right,
Yes.
like on the periodic
Right.
table. Okay,
Right.
cool, got it.
But we'll see an example of that. For now, I just want you to kind of start to understand the steps. So choosing our central atom, that's going to be carbon. So, okay, I'll put that right in the middle. Next, it's going to be surrounded by 4 different hydrogens. So I'll put a hydrogen, hydrogen, and a hydrogen. So that's done. Step 3, I do this a little bit differently. So at first, you're going to learn like the Lewis dot diagram where you'd see like, oh, carbon, we said has 4 valence electrons. So you're going to draw it this way if it's just on its own. And then hydrogen only has 1. So it could only make 1 bond. So these would combine together to then form 1 bond. So it would look something like that. And then you'd still kind of see that whole approach here. Like if I were to actually put, to show you this, that's carbon's Lewis dot diagram. I would do the same thing. I'm going to do this in blue for hydrogen. So just 1 valence electron, 1 valence electron, same thing here, same thing here. Essentially what's happening is they're going to form a bond because 2 electrons form a single bond. So instead of doing that each time, because it's time consuming, what I typically would just do is simply put a single bond already there, because this is telling us that they're going to bond regardless. Okay. But does that make sense? What I'm explaining there?
Yes, like the line.
Yes. Yeah. So, and it's just because like we're basically connecting the dots here. So it's going to form a single bond either way. So it kind of just saves you the step of drawing the Lewis dot diagram and then, connecting everything. I kind of like want you to understand that they're going to form a bond regardless. So that would be the next step. And then from there, the very last thing, part of step 3 is to just make sure that all of the electrons add up to what we did in step 1. So in step 1, we said that there are 8 total valence electrons, and we want to double check that that's true. So if I were to, I'm going to draw this in red. If I were to kind of recount these electrons, I would see, well, remember, 1 bond consists of 2 electrons. So there's 2 so far. So 2, 4, 6, and 8. So yes, that checks out. And because that's correct, because that checks out, we're done. That is the correct Lewis structure. So those are, I'd say, like the main 3 steps for a typical Lewis structure. That's what we would apply. Questions here?
No, that makes sense.
Perfect. Moving on to the octet rule. So we just drew our structure, and if we saw there was 8 valence electrons, that's what we said. So this actually follows the octet rule. And what the octet rule is saying is that the central atom prefers to have 8 valence electrons surrounding it. Like it's stable, it's happy. And we always want to make that central atom happy. So we can look at this again, and I'm just looking at the central atom, so carbon, and I'm seeing that there's 2 valence electrons here, so 2, 4, again, 6, and 8. Because there are 8 valence electrons surrounding that carbon, then I know, yep, this follows the octet rule. It's stable, it's happy. Once again, the structure is correct. So I'm going to keep applying this, okay? I'm going to keep applying the octet rule and the steps that we went through to draw a Lewis structure. So once again, let's just start with the first part where we're calculating the total number of valence electrons. How many valence electrons does phosphorus have?
5.
Yes. What about chlorine?
7.
Good. And then we'd multiply by 3 because there are 3 chlorines. So 21. We'd add these together. So 5 plus 21 is 26 electrons. So check. Next, we have to choose our central atom. What would be our central atom in this case?
Phosphorus?
Yes. And then another way too, when I said like, oh, the least electronegative atom is going to be your central atom, that will help you a lot when you have like larger structures. So like when there's typically like more than one central atom, which we'll go over. But that's something that we were going to see. For this case, we could have just seen that phosphorus is by itself. And the fact that there is a 3 subscript, that tells us that there's going to be 3 chlorine surrounding the phosphorus.
Oh yeah, so you can just look at it now.
Yeah, right.
Okay, that makes sense.
So our central is phosphorus. And then next, I'm just going to place a bond. So I said that there's 3 chlorine surrounding phosphorus. And then I'm already going to say, hey, this is going to add up. So there's a bond here, bond here. Now, I also want to talk about the different lone pairs. So lone pairs just mean that these are lone pairs. They're electrons that are not like on a bond. So they're still on that atom, but they're not actually within a bond. So let me show you this again. Just in the very beginning, I will draw the actual Lewis dot structure. So for chlorine, we said there are 7 valence electrons. So I'll say there's 1, 2, 3, 4, 5, 6, and 7. And I would do the same thing for every single one. Now, if we realize there's always going to be one here that's being shared with whatever element it's bonded to. And then there's going to be 2 electrons on every single side, essentially. So there's going to be 6 electrons, or 6 electrons, 3 lone pairs, if that makes sense. Like these are lone pairs. These are the 3 lone pairs on the chlorine. Is this making sense so far? Mm-hmm. Okay, cool. And I would basically do this all throughout for every single one, just showing you that there are 7 valence electrons on that chlorine. And then now I would look and see, okay, well, does phosphorus have 5 valence electron? Well, no, it doesn't, because here's 1, 2, 3. Now I need a lone pair, 5. So I could have seen it that way, or I could have done what I prefer to do, which is kind of like the faster way. So the faster way of doing this, and I'll show you again, was just to simply start with drawing the bond. Then from there, I see, well, actually from there, I'm going to actually draw the lone pairs on chlorine. And then something to note, every single, basically any single halogen, same with our oxygen, sulfur, and so on, those are going to also have lone pairs like this. You're going to see a pattern. So typically I'm pretty much just going to say for our halogens, you're going to constantly see a pattern with this where there's going to be 3 different lone pairs on that atom. So that's why I already knew that, okay, I just have to put all the lone pairs in, put a bond, and I'm almost done. The last step is then to know that, well, 1, this has to follow the octet rule, and it doesn't right now because there's only 1, 2, 3, 4, 5, 6 valence electrons on our central atom. It wants to have 8, so I add 2 more on phosphorus. Another thing I could have done to also check this, which is the end part, is seeing if all of the electrons add up. So I can just count this again. So I can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, I could do that if I truly wanted to. Or I could also do this, go a little bit faster here and just saying that this is 8 valence electrons. There's 3 here. So 3 times 8 gives us 24 plus the additional 2 here. I know there's so many things that I'm throwing, but this is essentially the concept of drawing Lewis structures.
Yeah, no, that makes sense.
Perfect. Okay, you get the point. And it looks something like this. I just want to leave it. Cool. Moving on. All right, so we saw that we can put lone pairs on the central atom. And then now we're going to go into just the different types of bonds. So just recall that when 2 electrons combine, that forms a single bond. When 4 electrons combine, that forms a double bond. And then when 6 electrons combine, that forms a triple bond. So I'm going to do the same sort of concept here again. Let's just identify the total number of valence electrons. So I'll start with carbon. How many are there?
There are 4.
Good. What about oxygen?
6.
Perfect. And I'll multiply this by 2, giving us 12. So 4 plus 12 gives us 16 electrons. And then what's our central atom?
Carbon.
Yes. And that's surrounded by 2 oxygens. And then again, I'm just going to place the bonds already there. So I did all this so far. Now I'm just placing a bond and a bond. And then I also know that oxygen is going to have these electrons surrounding it. Okay, these lone pairs. So if we notice, carbon isn't happy, okay, because it doesn't have a full octet. So it doesn't have 8 valence electrons surrounding it. So far, there's only 1, 2, 3, and 4. So what we have to do is we actually have to form a larger bond or a double bond. So how we do that is by actually moving electrons to then give us that double bond. So we're not adding an additional amount of electrons because this has to give us 16. And if we notice, this already has 16. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yep, I can't add any more electrons to that central atom. So instead, I have to form a double bond. And when I do this, I'm essentially taking these electrons and moving it to form that double bond. So there's no longer 3 lone pairs. There's now just 2.
Okay. I see.
And then this is something else to note is that if this were something that was just bonded to something that was like single bonded to an atom, then I would have 3 lone pairs. If this was double bonded, I would just have 2 lone pairs. If this was triple bonded, I would just have 1 lone pair.
Okay. Yeah.
So definitely beware of that, just because I have seen this where you add too many electrons or too many lone pairs and you do get the answer wrong, unfortunately.
Okay.
So, okay, perfect. And then we can check again and just see, yes, this does obey the octet rule because here's 1, 2, 3, 4, 5, 6, 7, and 8. That's happy. And then we didn't add any additional electrons. It's still 16. All right, this is another one that's a little bit larger, I'd say. So for this one, we're going to have multiple central atoms. And how I would approach this is just by seeing, well, there are several hydrogens, right? There's 4 hydrogens in this structure, but our central atom could never be hydrogen since that could only form 1 bond, since it only has 1 valence electron. So our central atoms can only be carbon and oxygen. But before I do that, I have to figure out how many valence electrons there are in total. So carbon has how many valence electrons?
4.
Good. What about oxygen?
6.
Perfect. And then hydrogen we know has 1. Don't forget about actually counting them all. So this is 3 plus an additional 1 at the end. So there are 4 hydrogens. 1 times 4 is 4. We'll add everything up. 4 plus 6 plus 4 gives us 14 electrons. And then we said that our carbon and our oxygen were our central atoms. So I'm going to draw it this way. Now, if you were curious and you weren't sure, how do I draw this? Like, how do I know where the hydrogens go? Like, what does it bond to? Well, this is typically written in the form that it wants you to draw the structure. So this already is telling us that there are 3 hydrogens on this carbon. So I would surround this as follows, and then same goes for the next one. This is already telling me, oh, that OH, that H is going to be together. So that's how I would put a bond for everything. And I'm not done yet. So then I would then look at the octet rule and see, is carbon happy? Does it have 8 valence electrons on the central atom? And I would see that, yes, it does, because here's 1, 2, 3, 4, 5, 6, 7, 8. That checks out. Our other central atom is oxygen. And now that has to also have 8 valence electrons following the octet rule. And it does not, because this only has 1, 2, 3, and 4. So instead, we would have a lone pair. 2 lone pairs, actually, to give us 8 valence electrons. Now this is complete. Questions?
No, that makes sense.
Perfect. Next one. Okay. So with this one was actually on one of your slides or in class assignments. And just a note, they did give you a hint. They did tell you that the oxygen was bonded to this carbon. So just a note, because I know I just said for the last one that they typically will give you, like this is already written out the way you should bond it to. Like these hydrogens go with this carbon, this hydrogen goes with this oxygen. Okay. This one actually had to tell you that this oxygen goes with this carbon. Yeah. Okay. That's not just like, you're magically going to know. No, they would have to explain that. So once again, let's just calculate how many valence electrons we have. So I know you know this by now, but you're going to see this a lot. These are probably the most common atoms that we're going to see are carbon, hydrogen, and oxygen. Carbon we said has 4. There are 2 carbons in this case. So 8. And then for hydrogens here, there's 3 here plus this additional 1. So there's 1 valence electron times the 4 hydrogens, so 4. And then there's only 1 oxygen, so 6. So I would add this all together. So 8 plus 4 plus 6 gives us 18 valence electrons. And then now looking at this, what's our central atoms? So we're going to have two central atoms. What do you think are the central atoms?
So carbon is one of them.
Good.
Can we have carbon again?
Yes, we can. Perfect. Yes, okay. We can. And if you were trying to, actually, this goes back to the rule I was talking about, where if I'm trying to decide if carbon or oxygen is like the other central atom, we would say, well, which one is the least electronegative? Oxygen is the most electronegative. Carbon is the least electronegative. So I know that the other carbon also will be our central atom.
Okay.
Perfect. And then next, I'm just going to see that these hydrogens go to that carbon. So I'll place them around that carbon. This originally told us that this oxygen will be bonded to that carbon. So I'm just going to put that on top. And then I'll put the hydrogen next to the carbon. And then once again, I'm just going to build this just by adding single bonds all throughout. This is a little bit too long. Okay. And then from there, I'm just going to double check if we have 18 valence electrons and if this obeys the octet rule. So for carbon, this does obey the octet rule because this has 2, 4, 6, and 8 valence electrons. Next, for this carbon, it does not because this only has 2, 4, and 6 valence electrons. So what I would need to do, and something to note, was just remember this oxygen has 3 lone pairs. So if carbon isn't happy, meaning it doesn't have 8 valence electrons, it's not following the octet rule, it wants to have a greater bond, so it wants to have a double bond. So I would just move one of these electrons here to form that double bond. Okay. And now this is complete.
So would it be wrong if you just decided to add a lone pair to the carbon itself?
Yes. Yes, it would.
Why?
Because, here.
Oh, then we're adding electrons.
Yes,
oh, okay.
Exactly. Then we have 20 valence electrons. Exactly. So you always want to have the total number of valence electrons. That's why that's the first step. And then another thing, that's actually like the main reason. We always want to just kind of like, we're moving around the electrons just to get the best structure. Like that's essentially what Lewis structures are. Like we're just trying to build the best, most favorable structure.
Okay.
Cool. And there's exceptions, of course.
Oh my gosh.
So, I know. But luckily these aren't that terrible. Okay, there's going to be 2 main exceptions to the octet rule. So we could have an incomplete octet, meaning there's going to be less than 8 valence electrons on the central atom. And I'll tell you how you can just easily tell. So the ones that will have an incomplete octet are basically going to be the atoms that don't have 4 valence electrons to begin with. So remember, Carbon has 4 valence electrons. These had 3, these had 2. So what I'm looking at is I'm literally just looking at the groups that do not have 4 valence electrons. And the reason why I just highlighted boron and beryllium is because those are the most common ones. So those are typically the exceptions to the octet rule that you will see. That's pretty much it. So I literally would say those are the main ones that they always use. But just knowing that they're always going to have less than 4 valence electrons to begin with. That's how you know it's going to be an incomplete octet.
Okay.
And I'll show you an example. So how many valence electrons does boron have?
3.
Good. What about fluorine?
7.
Perfect. So 7, I'm going to multiply this by 3 because there's 3 of them. So 3 plus 21, that gives us 24 electrons. What's our central atom?
Boron.
Perfect. I'm going to surround this by 3 fluorines, putting our single bonds already, putting the lone pairs, knowing that halogens will always have those 3 lone pairs. And then now I'm just going to double check that I do have 24 electrons. So how I could easily do this is just by seeing that this is 2, 4, 6, 8. So this is 8. This is also 8. 8 times 3 does give us 24. So that checks out. But I know that this is an incomplete octet because there's only 2, 4, and 6 valence electrons on that central atom. But it's happy. It's totally fine. So we would just leave it like that. That is the best structure. That is the correct structure.
Okay, so the exception meaning that I get what you're saying, so it's less. Okay, cool.
Yes, exactly. And then the other one is the opposite way. There's more. So it's an expanded octet. There's more than 8 valence electrons on the central atom. And I'll explain what that would be. So the place that it's going to actually start is going to be the 3rd row. So this is the 3rd row, but specifically it's going to be here. So the 3rd row and then below. So in your book, it's probably going to say the 3rd row and above. And though that's correct, mentally, that doesn't make sense because this is row 3, right? And we're thinking, oh, if this is row 3, it would be above it, right? 3 and above. And that's not how you're going to think about it, right? So I like to think about it as it's row 3 and like physically below everything
That makes way
else.
more sense, yeah. Because I would totally be thinking that. But are they saying that because like based on the energy levels of being like 3,
Yes,
4, 5?
correct.
Oh, okay. That makes
Exactly.
sense.
That's how they're basing it, yeah. So, but I just prefer to kind of box it up and say, these are the main ones. Just know that these are your exceptions. So I typically say, 3 and physically on the periodic table below, So the main ones that I always see, and I wrote that down. So the examples that you're probably always going to see are phosphorus. Let's see, all of these, hold on. And sulfur is one of them as well. These are probably the most common ones that are going to be used. Now, something that I want to make a point here. These all have the possibility or potential to form an expanded octet. It doesn't mean that every single time they will. And I'm going to highlight back to one of the ones we just did. So phosphorus has the potential to form an expanded octet if it needs to. But as we saw previously with this example, it didn't have to, right? This had already, 2, 4, 6, 8. This obeyed the octet rule, and that was fine. However, if I needed to add, if there was 5 chlorines, then I would see, okay, this does have that possibility of having that expanded octet if it so needed to. So it's based on whatever atoms are attached to it.
Okay.
Okay, we'll do some examples there. Versus, let's say boron or beryllium, they're always going to be incomplete. It's not saying that they have the possibility. No, those for sure are incomplete. They're not going to obey the octet rule. So here's an example for an expanded octet rule. So let's just look at how many valence electrons we have again. So for xenon, how many valence electrons does that have?
It has 8.
Good. What about fluorine?
7.
Perfect. Good, and then we'd add these together. So, and I just found the 4 from here. So 28 plus 8, that would give us 36 electrons. Okay, what's our central atom?
Xenon.
Good. We know this is going to be surrounded by 4 fluorines, so I could draw it like this for now. I'll put our single bonds. And then, of course, any sort of halogen is going to have 3 lone pairs. So just putting them all. Perfect. And then we're going to count and see, does this have 36 electrons? So this has 8, right? 2, 4, 6, 8. That's 8 times 4 of them. So 8 times 4 gives us 32. We need more. So this right now only has 32 valence electrons. We need 36. So because of that, we need to add 4 electrons. So that means we're going to add 2 lone pairs on the central atom. So that's something to note, is whenever you basically put all of the electrons on the elements that are like surrounding it or on the outside, and if you don't have enough valence electrons, then you come back to the central atom and add more.
Okay.
And then that's how, in this case, we do have 36. We will see that this is going to be an expanded octet because this has 2, 4, 6, 8, 10, and then 12. So this actually has 12 valence electrons surrounding it, but that's completely fine because it is part of the exception right here.
Okay.
All right, we're going to keep going and we're going to see Lewis structures of ions. So now we're adding a charge. So this is basically going to be the same sort of concept where, remember that cations, we're actually going to lose an electron, meaning we're going to subtract an electron. And then anions, the negative charge, we're actually going to add an electron. So we're going to add. So in this case, since we have that positive charge or a cation, we're actually going to have to subtract 1 electron at the end. So the first thing we're going to do is just identify how many valence electrons do we have. So how many are there for nitrogen?
There are 5 for nitrogen and 1 for
Good.
hydrogen. We're multiplied by 4 though, so there's 4.
Mm-hmm. Good. So 5 plus 4, and then we would subtract 1 based on this 1 plus 1 charge. So subtract 1. And then instead of having, instead of having 9, we're actually going to have 8. And then that's something to also note. You're not going to be having like an odd number of valence electrons, because that would mean that we wouldn't have a pair, like a lone pair. So if you were to see that, I'd say double check. Most likely there is a charge that you're forgetting to apply. So that's why in this case, we had to have this charge to reduce that number from 9 to an actual even number of 8. What's the central atom?
Nitrogen.
Good. I'm going to surround that by 4 hydrogens, placing a single bond all throughout. And then I'm just going to double check if this gives us what we wanted. So let's see, this is 8. So 2, 4, 6, 8. Yep, that checks out. The last thing, so the only difference now is that we have to actually place the entire structure in brackets and place the charge on top. This is whenever it's a charged or an ion, essentially. Whenever this is an ion, you have to put the Lewis structure in brackets and put the charge on the outside. It would be marked wrong if you didn't.
Okay.
We'll do the same thing for this next one. So now we have an anion, and I know that I'm actually going to add an electron. So go ahead and let's figure out again how many valence electrons we have. So how many valence electrons for chlorine?
Chlorine has 7 and oxygen has 6.
Good. And then multiply that by 4. Okay. And then I'm going to add 1 more electron. So 7 plus 24 plus this 1. Let's see. What does that give us? So This gives us 8. 24 plus 8, 32.
Okay, I'm glad you're not asking me to do that. I can't do quick math. I need my calculator for that simple stuff.
But I'll have you do, I'm going to have you do practice problems after, but that's fine. You can use your calculator to calculate it. That's not a problem. So what's our central atom in this case?
Chlorine.
Yes. Perfect. And then we're just going to place oxygen surrounding it and placing our bonds. The oxygen's going to have 3 lone pairs all throughout. And then we'll double check the amount of electrons. So in this case, I have, again, this is 8. 8 times 4 does give us 32. That checks out. The last step is to just place this in brackets and then our charge on the outside. So perfect. Keep practicing those steps to drawing Lewis structures that we covered. Take notes and really just give this all you got, because we're kind of in the middle of the semester right now. And you know what? I know you can do this. I know you don't want to repeat this class. And quite frankly, you're capable of doing this. And you know it too. You just really need to believe in yourself. So keep going. Try out the next questions in the next video.